Now we'll be looking at how to derive different quantities from the Schrodinger's equation, from the wave function, I'm sorry. We're not going to see what exactly the wave function is. For example, going back to our previous example of f of x equals x square plus y square, let's say f of x represents the wave function, then we are not going to see that f of x equals x square plus y square. We're not going to see what f of x is equal to actually. We don't get the expansion of the wave function. It is beyond the scope of our course. What we'll see is, given the value of f of x, how am I going to get back y? How am I going to get back? I take f of x minus x squared whole raised to 1 by 2. So that equation, or given the value of the wave function, how do I derive the quantity I want? That is what we are going to see. So for all intents and purposes, the wave function, the actual expression for the wave function can be anything. We are not going to focus on that. So we come back to our derivation here. Any moving particle is associated with a matter wave. This again was a statement we discussed in one of the previous lectures. It basically says a moving particle is expressed in terms of a wave packet, which denotes both the wave nature as well as the particle nature. So, and to describe a wave or a particle for that matter, you need an equation, right? So again, like I said, for a wave, your equation will be in terms of frequency and amplitude. For a particle, it will be in terms of position and momentum, and because of the uncertainty principle, it will also involve a wave function and probabilities and all that. But at the end of the day, to describe an entity, you need an equation, and we are going to call this wave function as psi of x comma t. This symbol you see here is called psi, psi. It's pronounced psi. So, and that is again a formal notation. You can call it f of x comma t, g of x comma t, anything, but the standard notation used is psi of x comma t. So again, we are not going to see what exactly is the expansion for this equation. We are only going to see how we use it to derive what we want. So it was discovered experimentally that only a certain class of functions which satisfy this equation can be used to describe a wave. And what is this equation? The second derivative of a function with respect to x should be equal to 1 by c square times the second derivative with respect to t. So I'll explain this. So basically we'll try to understand this with a toy example. So let's say I'm giving you three functions. One is f of x equals x squared plus y squared. The other is x cos y minus y sin x, something. I'm just giving you random functions. And the third one is, let's say, e to the power minus x by y, something. So they tried substituting each of these expansions to psi of x comma y, and they tried performing experiments to see if this is the correct expansion. And they understood that only certain expansions satisfy all the experimental results which they got, meaning they would expect some results, right, from an experiment, and then they observe some results. So only when you take certain functions as psi of x comma t, the expected and the observed values match each other. And what are those class of functions? Those are the functions which satisfy this equation. And what is this equation? I take an expression. The second derivative of that expression with respect to x should be equal to 1 by c squared times the second derivative of that expression with respect to t. So it should be an expression in terms of x and t. So only the expressions which satisfied this rule were experimentally determined to be an accurate description of a particle. So they discovered that only the functions for which this rule holds true are valid functions which can be called the wave function. Now for which functions did this rule hold true? That again, it was mathematically described that any function which can be expressed in this form satisfies this equation. What is this form? Psi of x comma t equals a e raised to minus iota times omega t minus phi. So you take a normal function like x square plus t square, or x sin t minus t cos x, or e to the power minus x by t. Those functions do not satisfy this rule. The only functions that satisfy this rule are of this type: a e raised to power minus iota omega t minus phi, where a is some constant, e raised to power minus I is the square root of minus 1, omega is your angular frequency, t is time, and phi refers to phase. So only the functions of this type satisfy this equation. So the actual expansion for your psi of x should be something of this form. But what exactly is the a value, what is the phi value, and so on, we will not be looking at that. It was experimentally determined that your expansion for psi is something of this type. So we accept it as true and we go on. We use this to find out how we can derive whatever we wanted. So omega is 2 pi nu, where nu is your frequency, and your phase can be written as 2 pi by lambda times x. So that is what we do here. We substitute the values: a e raised to minus I, 2 pi nu t minus 2 pi by lambda into x. 2 pi nu is omega and phi is nothing but 2 pi by lambda into x. So I take the 2 pi out, common factor, a e raised to minus I into 2 into pi, nu t minus x by lambda. This is nu frequency, not v velocity. Please keep that in mind. Yeah, so from this equation is what we currently have. Now here we have frequency and lambda. We're trying to bring it down in terms of constants as much as we can, because if you look at this equation, 2 pi I are constants, but v, t, x, lambda, nu, t, x, lambda are all variables. So we try to bring down the equation to as few variables and as many constants as possible. So we know E is equal to h nu, so nu can be written as E by h, and again lambda equals h by p, so 1 by lambda can be written as p by h. Again we do that substitution, we get this is what we already have, and instead of nu we put E upon h here, and instead of x by lambda we put x divided by h by p, which is px by h. So when we make that substitution we get this, and since you have a common h in the denominator, you bring that out, you get a e raised to minus I 2 pi by h et minus px. And now this is one assumption, one standard assumption we make: h cross is nothing but h by 2 pi. This is just for convenience, so you can write h by 2 pi at every step, but because everything is a constant, you just for simplification in terms of writing, we assume h cross as h by 2 pi. So because you have h by 2 pi in the denominator, it becomes a e raised to minus I by h cross et minus px. So what did we do here in this slide? Basically it was determined that the only set of functions which accurately describe a particle are those for which the second derivative with respect to position is equal to 1 by c squared times the second derivative with respect to time, where c is the speed of light. And which were those functions? The functions which satisfy this equation. Here we replaced omega with 2 pi nu and phi with 2 pi x upon lambda. We brought the common factors out. We wrote nu and lambda in terms of h. Again we brought the h outside, and we replaced h by 2 pi with h cross. So finally our expression for wave function which we have now is psi of x comma t equals a e raised to minus I by h cross times et minus px.